Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, when approved, if we have p greater than 3 is a prime, we want to show that the expression 1 plus 1/2 plus 1/3 all the way to 1 over p minus 1, which we can express as some fraction a over b, where the greatest common divisor of a over b is 1. Then this expression a over b, p squared divides a. So the first thing we're going to do is sum our expression in a special way. First thing we're going to note is 1 over k plus 1 over p minus k is p over p minus k times k. Note p is an odd prime, so we have an even number of terms here. We can pair them up into p minus 1 over 2 different pairs. And each one of these pairs turns into something in the form p over p minus k times k. P minus k and k are both relatively prime to p because they're less than p, and p is a prime. So now we know we're going to have at least p divides a. So we're going to take out p and our new sum. So now we want to show that the sum, once we pair up our fractions and factor out p, the sum from k equals 1 to k equals p minus 1 over 2 of 1 over p minus k times k. We want to prove this sum when we express it, again, as a reduced fraction. The numerator has the divisor of p. And so we're going to pass to the field zp, so we're going to look at everything modulo p. And so this fraction, we can turn it into just p minus k is congruent to minus k. 1 over minus k is the inverse of minus k, which is just minus k inverse. 1 over k becomes k inverse. So this thing becomes a sum from k equals 1 to p minus 1 over 2 of minus k minus 2 squared, which we can do because there's no divisor of p on the bottom. So we're not dividing by 0 anywhere. So now we want to show that each one of these k to the minus 2 squareds, none of them are congruent to each other. And so that we have the sum of all possible squares. There are p minus 1 over 2 possible squares in modulo p. I want to prove that we have all of these in this expression. So first assume we don't. So assume we have some a, b in our set of numbers from 1 to p minus 1 over 2, such that minus 1 minus a to the minus 2 is congruent to minus b to the minus 2. So we're going to bring b over to the other side, add b to the minus 2, factor it as a to the minus 1 minus b to the minus 1 times a to the minus 1 plus b to the minus 1 congruent to 0, mod p. So mod p is a field, so if we're assuming a does not equal b, so assume a to the minus 1 minus b to the minus 1 is not congruent to 0. So we can divide that. So then we have a to the minus 1 plus b to the minus 1 is congruent to 0. Or a to the minus 1 is congruent to minus b to the minus 1. Multiplying by ab, we get b is congruent to minus a. But note, take any a from 1 to p minus 2, minus a falls between greater than p minus 1 over 2 to p, so that we cannot have this. We can't have this. So in this case, we have a minus 1 is congruent to b minus 1, in which case, multiplying by b again, you get a is congruent to b. So from this, we have that our sum from k equals 1 to p minus 1 over 2 of minus k to the minus 2 squared is really congruent to minus k equals 1 to p minus 1 over 2 of k squared. Because this k minus 1 just k minus 1 squared, it just takes all the possible squares. These are two different expressions of the same set. So these two are equal. And then summing using the formula for the sum of squares, we get this is equal minus p minus 1 over 2 times p minus 1 over 2 plus 1 times p over 6, and this expression is congruent to 0. So this expression, so 1 over p minus k times k must be congruent to 0. And so this sum sums up to something in the form a over b, and b minus 1 is congruent to 0. B minus 1 is not 0. B is not 0. So b minus 1 is some non-zero number. So therefore a is congruent to 0, and p must divide a. And because we already pulled out p earlier, we have p squared must divide the numerator of this whole expression. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.